Hi guys, this is Amar and welcome to Network Engineer Stuff. So guys, in this video, we are going to focus on OSPF chapter 1 introduction. OSPF, that is Open Shortest Path First. Now, this routing protocol is a very important routing protocol. It's an super useful routing protocol and it's widely used routing protocol. It is very commonly used routing protocol. So studying OSPF guys is super important. OSPF guys comes under this category of IGP, that is Interior Gateway Protocol. So when we say IGP, we mean to say that it will work within the same autonomous system, that is within the same AS. OSPF is an open standard routing protocol. It's an industry standard routing protocol, so it can be used on multi-vendor devices like Cisco, Juniper, Huawei, Arista, etc. So it will be used. It is supported on multi-vendor device. That is the main, I'll say, an important thing which is about OSPF. Another point which I've mentioned in this slide is that which you should know is that OSPF uses protocol number 89. So this is the protocol number of OSPF 89. Link state routing protocol. Yes, OSPF is a link state routing protocol. So when we say OSPF is a link state routing protocol, we mean to say few things about OSPF, that the updates in this category of or this type of protocol is that the updates are triggered. So when I say the updates are triggered, I mean to say that once there's a change in the network topology, I mean to say the change in network topology in terms of some link goes down or up, there's some change in the metric, some neighbors added or removed, etc. Then the router immediately sends an update to inform its neighbor about that change. That is triggered update. Okay, so I have wrote here the updates are triggered and not periodic. When we say periodic, the updates will be sent after a particular interval of times. But when I say triggered, it will be sent as soon as there's a change in the network topology. I'll try to explain you with help of a diagram, a small topology. Let's say this is router R1 and let's say this is router R2 and OSPF is running between them. Okay. And let's say there's some segment, some prefix, let's say 10.1.1.0/24. For some reason, let's say this network goes down. Now, as soon as this goes down, R1 immediately will send the update to its OSPF neighbor, that is R2, that this particular network is down, that is 10.1.1.0/24 is down. So it sends it immediately. So I've wrote here triggered update. So triggered update because it's triggered by an event and it's not periodic. So because of this kind of nature of OSPF, the convergence is fast. The convergence is fast because the updates are triggered. As soon as something goes down, the update is sent to the OSPF neighbor. Again, the updates are incremental. So when we say the updates are incremental, we mean to say that OSPF will not send the entire routing table as an update every time in the update, but it will send only the topology change in that update. So let's say if we take the same example, let's say there's one more network 20.1.1.0/24 and let's say this network goes down. So OSPF will send the update only regarding this particular network which is down, okay, which is like which have undergone some change, right? So it will only send that incremental update and not the entire routing table as the part of an update. Again, in OSPF, the updates are multicast. So when we say multicast, we mean to say that these updates are sent to the entire group. So what is the benefit of the updates being multicast? Let's say they're in this particular domain or in this particular area, there are multiple routers. Okay. Now this router 1, router 2, router 3 and router 4. Okay. So this router 1 is running OSPF, router 2 is running EIGRP, router 3 is running OSPF, router 4 is running EIGRP. So when I say the updates are multicast, so the updates on router 1 will be sent only to R3, which is in OSPF, which is in its domain. Okay. It will not be sent to non-OSPF devices, okay? Because if it is sending to a non-OSPF devices, it is unnecessarily wasting the CPU cycles of that non-OSPF devices, because it will be updating, it will be like processing those updates unnecessarily, and it will be resulting unnecessary CPU cycle utilization on those routers. So there is no need for that, right? So that is the reason the updates are multicast in OSPF, and this is a big advantage in OSPF. It uses this multicast address which I have mentioned, 224.0.0.5, 224.0.0.6. So these are the two IP addresses which OSPF uses. Of course, there are some exceptions in it. When the adjacencies first been getting formed, there's some message which will be unicast to a specific neighbor. Again, we will understand those things more in details as we go on studying this particular series. The other point, OSPF is classless routing protocol. So when we say classless routing protocol, means whenever the OSPF router will share routing information with its neighbor, at that time it will share subnet marks information also with that neighbor for that particular routing information. Like, let's say this is R1 OSPF router, this is R2 another OSPF router, they are neighbor, OSPF neighbor. Now if let's say there's a route in the routing table of R1 and R1 want to set the update of this particular route to its OSPF neighbor R2, it will send the subnet marks. This is the subnet marks in the update. So this is very important point to remember, and this is the reason why OSPF support CIDR, that is classless interdomain routing, and VLSM, which is variable length subnet marks. Moving forward, OSPF neighbors. So when we talk about OSPF neighbors, OSPF routers typically forms neighborship between directly connected routers which are on the same network segment, or I can say which are in the same subnet. Okay, so let's say this is like router R1, router R2, R3 and router R4. The connectivity is like this. Now this particular router R1, okay, R1 can form OSPF neighborship with R2 and R4 because they are directly connected to R1. R1 can form OSPF neighborship with R2 and R4 because this R2 and R4, both these routers are directly connected routers. They are in the same subnet. They are in the same network segment. They are in the same subnet. So that is the reason they will form the neighborship with R1. But R3 cannot form neighborship with R1. OSPF neighborship cannot be formed between R1 and R3. So this is a very important point to be remembered. And of course, the a few criteria for what OSPF neighborship should happen. So one of the criteria is this. So we'll study those in details in further videos as well. OSPF end-to-end visibility. OSPF routers have end-to-end visibility in the form of topology table. So this topology table, what is this topology table? So topology table is, guys, nothing but it will basically have a list of all the possible routes to reach all the networks within that area. What is the area we'll study later on. But topology table, guys, to remember is that it will have it is basically a table which will have all possible routes to reach all the networks. So OSPF have this kind of table which gives it end-to-end visibility of the entire network. I'll again try to explain you with this same diagram or the same topology, R3, R4. Okay. Now let's say this have a network of 30.1.1.1/24. Now this is the subnet which is connected to R3. Of course, there's OSPF neighborship between R1 and R2, OSPF neighborship between R2 and R3, OSPF neighborship between R3, R4, and OSPF neighborship between R1 and R4. So there's this OSPF neighborship is going on. Of course, R1 will learn about this particular network. R1 will also have this particular network in its routing table. So it will be learning that network via two different routers, OSPF routers. One is of course R2 and one is of course R4. So it will be having two routes. One route will be this. So this will be a route 1 and the other route will be via R4. Okay, so this will be route 2. So in the topology table of R1, in the topology table of router R1 for destination 30.1.1.1/24, it will be having route 1 and route 2. So it will be having two routes. Okay, so let's say there's some another destination. Okay, so for that destination also it will be having all the possible routes. There's some another destination. For that destination also it will be having all the possible routes. So this forms our topology table. So topology table contains a list of all possible routes to reach all networks. That is topology tables, and which gives OSPF end-to-end visibility of the entire network. And there's an algorithm, Dijkstra. So currently the picture is of Sir Dijkstra. He is the guy who actually invented this algorithm, and OSPF uses this algorithm, that is Dijkstra algorithm, Dijkstra SPF algorithm, that is shortest path first algorithm. And what this algorithm does is like this is a topology table, right? So it will be working on this topology table and it will be finding the best route to reach all the net destinations. So let's say for this destination 30.1.1.1/24, let's say this route is better route 1. So it will be putting this route in the routing table. So the routing table will be like this. The routing table of R1 will have, like, for the destination 30.1.1.1/24, route 1 is the best route, so it will be in the routing table. Of course, for some other network, some other route will be best. So it will be having best routes in its table, and that table is known as a routing table in OSPF. So this routing table, the algorithm basically which find out the best route is Dijkstra algorithm. And of course we should have a lot of respect for Sir Dijkstra. Table. So we talked about this table, a routing table, topology table, of course, and of course the neighbor table also. So neighbor table will be the list of the OSPF routers which are its neighbor. So for R1, as we discussed over here in this particular diagram, so the neighbor table of R1 will include R2 and R4. That will be its neighbor table. AD value. Now the routes which are learned via OSPF, will have the AD value of 110. So this is the AD value. Now guys, many of you know the AD value, what AD value is. I won't go into the basics of CCNA. So whatever routes are learned via OSPF, guys, do remember, this is a very important interview question as well. The AD value of the routes learned via OSPF is 110. Metric. In OSPF, metric is cost. So this cost basically depends upon bandwidth, and this cost is inversely proportional to bandwidth. So whenever I say it is inversely proportional to bandwidth, I mean to say that greater the bandwidth, less the cost will be, and less the cost, the path will be better, it will be preferred. So in OSPF, metric is cost, and the cost depends upon bandwidth. Cost is inversely proportional to bandwidth, which means that greater the bandwidth, lesser the cost, and better the path is. So guys, do remember this point. This is a very important point in OSPF. So this is the formula of cost. Cost is equal to 100 divided by bandwidth in Mbps. So let's say there is a link which is having a bandwidth of let's say 10 Mbps. Okay, so the cost will be 100 divided by 10. So it will be 10. So the cost for a 10 Mbps link in OSPF will be 10. So let's say if the bandwidth is 100 Mbps. Okay, so the cost will be, of course, 100 divided by the bandwidth in Mbps, which is 100. So it will be 1. So for the link with the bandwidth of 10 Mbps, the cost will be 10, and for the bandwidth of 100 Mbps, the cost will be 1. So I'll also explain you with some example. Let's say this is router R1. The same topology we will take R2, R3, R4. Okay. So let's say this particular link have the bandwidth of 100 Mbps. This have a bandwidth of 100 Mbps. Between R3, R4 also 100 Mbps. But between R1 and R4, let's say it is 10 Mbps. So the cost of this will be 1 because it's 100 Mbps. For this also 1. For this also 1. For this it will be 10 because it's a 10 Mbps link. Now let's say to reach that network, here there is some network, let's say a 30 network. Okay. To reach this network, we have two routes, route 1 and route 2. This is a route 1 and this is route 2. So for route 1, what will be the total cost to reach this network? 30.1.1.1/24 from R1. The total cost will be 1 plus 1, which is 2. And for route 2, which is via R4, the cost will be, of course, of this link is 10 and of this link 100 Mbps is 1. So it is 10 plus 1, which will be 11. Of course, this cost is less. So route 1 will be selected. So the traffic will be going via R2 to R3. So route 1 will be selected and it will be put in the routing table. So this is how the cost calculation is done in OSPF. So guys, always remember, in OSPF, metric is cost and cost depends upon bandwidth, and cost is inversely proportional to bandwidth, which means greater the bandwidth, lesser the cost, and better the path is, as we have seen for route 1. So guys, this was the introduction chapter. I'll stop here, but before stopping, if you have any queries, if you want any notes or the other things, you can of course WhatsApp me on this particular number 8828002605. You can mail me on Gmail, networkengineerstuff@gmail.com. Of course, you can visit my blog, which is not very famous, but guys, please do make it famous. www.networkengineerstuff.blogspot.com. Of course, many people are following me on Instagram. If you're not following me on Instagram, please do go on Instagram and check for Network Engineer Stuff and start following me on Instagram as well. And of course, I have a YouTube channel on which you are watching this video, which is Network Engineer Stuff. So guys, please do subscribe to my channel and please do share these videos with your friends, colleagues, and help them in understanding OSPF much better. And if you like this video, please do comment and like this video as well. So I'll stop, guys. I'll catch up in the next video. Till then, bye, thanks, and keep studying. Best of luck. Thank you.